This video is about tensor product attention in LLMs. We're going to look at a paper that was recently written about how we could reduce the number of operations in attention. And we'll compare that to traditional multi-head attention. So this is the paper we'll be exploring called Tensor Product Attention is All You Need that was recently published. So let's start with an example. Suppose I were to query an LLM, the cat sat. The first thing that happens is that this gets converted to a set of tokens. We're going to build an input sequence. The first step is to go into our embedding matrix and figure out which vector corresponds to each token. So we're going to do a lookup. We're going to take the first token and map it to a row, which gives us a vector uh, of certain number of components determined by its dimension. So the dimension is fixed when the LLM is designed and differs by different LLMs. So when we do a lookup for each of the tokens, we get an input sequence, and we could convert this and look at it like a column vector. It's going to be useful because we're going to do some dot product operations with this during multi-head attention. In traditional multi-head attention, you have a certain number of heads, which is fixed during the design of the LLM. So as an example, suppose we had three heads in this multi-head attention architecture. Each one is responsible for different things. The first one is responsible for syntactic relationships. The second one is maybe responsible for semantic relationships. And the last one looks at positional patterns. So for each head, what we're going to do is figure out what the query key and value is. We're going to use the weighted matrices and perform a dot product operation on each vector that we map to. So when you look at these weighted matrices, they're trained during the training process that we're using during inference. And what do these query key and value mean? The query means, what am I looking for? The key means, what do I contain? And then the value means, what information should I pass along? So one of the challenges when doing these operations is that there's a lot of transformation and takes up storage, temporary storage, when you're doing these operations. So you may get a really, really big matrix in the end. So what we're going to explore with this paper is that how do we reduce storage? How do we reduce the transformations that we're doing to two? And like to fewer, how do we reduce the transformations that we're doing? This is where tensor product attention comes in. This is what this paper is proposing, an approach. So let's compare this to the traditional approach. In traditional MHA, the architecture is that you have a token and you're doing these operations, these dot product operations to figure out the query key and value. So here I'm doing multiple operations to figure out the query for each vector that I have mapped to. And in this example, I have 32 separate transformations, and we'll look at how this gets reduced to two transformations in tensor product attention. So the architecture in TPA is that you have a token, and what you're calculating is basically two things. One is the one is basically the B factors, and then the other thing is called the A factors. And we'll look at what this is. So these are two transformations that we're going to do, which significantly reduces the memory overhead. So the first thing, this is called head dimension. These are called A factors. And these right here are the ones that are called B factors. So these are separate weighted matrices that would be trained. So what you're doing, what you get in the end are these results that you could combine using tensor products that I'll show you. And these are the weighted matrices. So the way you combine the results of these two transformations is using the tensor product. There's something else to know is that this is just an example of a query for a single head, but you would also scale this out and do this for each of your heads. So you'll do this for the query operation, also for the key and the value. And it still reduces the total number of transformations you have to do. So let's look at how you combine the results of these dot products. So the way you do it is by using tensor products. So this is a notation right here, which is product, and what you get in the end is the query. So the one question that comes up, what is a tensor product itself? So in machine learning and LLMs, a tensor is treated as a multidimensional matrix, but that definition works for LLMs, but mathematically it's more than that. It's basically an object that is basically invariant under a change of basis. So let's look at what a tensor product is. So imagine you have two vectors spaces. One vector space is V, which has a basis of a finite basis of m dimensions. Another vector space W, which has a basis of m dimensions also. And we know how to construct elements of these vector spaces by using linear combinations. So another example is that when you look at the embedding matrix, all the vectors in there also form a vector space when the dimension D is defined by the design of the LLM. So how do we combine like these two vector spaces form their product? And this is what tensor products come in. So V cross W is actually a new vector space. And elements of this vector space are constructed by using bilinearity. There are a set of rules that allow me to construct and figure out what element belongs to this vector space. So this is a way to combine two vector spaces together. And their combination of their bases looks like this, E, F. Though this vector space, the dimension of it is m times m dimensional. So it's the product of the dimensions of v and w, and that's the dimension of this new vector space. So let's look at how you combine both of them. So here's an example of the combination of their bases like this, E1 tensor product with F1, and it goes on and on. So let's look at a concrete example of actually combining both of these vector spaces. So suppose the vector space V had an element like this, 2E1 plus E2, and the vector space W had an element like this. So how do you combine both of those? So there are certain rules that you would need to follow to combine things, which are called bilinearity combinations. These are the rules right here. And these rules tell you how to figure out what element will be in this new vector space given two vectors. So if I were to look at both of these vectors and combine them, it would look like this. So if I were to follow those bilinearity rules and do the combination, do their tensor products, and this is the new element, this is an element of that tensor product of this new vector space. And this is what it looks like. You'd see that it has its own basis vectors, and the basis of this new vector space is basically m times n, where m is the basis dimension of v and n is the dimension of w. So when going back to how this is used in tensor product attention is that we get a certain set when we do these operations, when we figure out what the A factors and B factors are, in order to combine them together to get the query, we're going to form a tensor product. So you could think of these as two vector spaces that were basically, which have different dimensions that we're basically combining together using a tensor product. So this is like tensor product factorization. We would do this for a query, key, and a value. So if we take a step back, you'll see that this reduces memory consumption. It reduces our transformations that we have to do in this very simple example. So this is what tensor product attention is about. This paper is called Tensor Product Attention is All You Need. It's very mathematical, technical. Highly encourage you to check it out. And in the next video, explore more papers on recent papers in LLMs and AI. Thank you.